the lecture of Rémi Monasson, diving deep into the replicas. So let's go for it.
Okay, thank you, Lenka. So what I would like to do today is actually first do a brief reminder of what we did yesterday, which was actually trying to illustrate on a model that we solved exactly how replicas can find back the correct solution. And I would like also to show you, to illustrate the notions about, the other parameters of replicas, the similarity between different solutions that you throw in the same landscape, as I explained yesterday. And also how we can actually manipulate the number of replicas to get detailed information, statistical information about the full probability distribution of the model. So I will explain this in detail at the end. Okay, so I will start with a reminder about yesterday. So I was interested in the so-called spherical spin glass problem or model. So it's a highly relaxed version of the of spin glasses, where we start from so we have n spins, or let's say variables if you prefer, but I use the standard vocabulary here. We have a W matrix, which is the n by n W matrix, which is GOE, so the Gaussian orthogonal ensemble, and to be more precise, WII is a normal variable of variance 2 sigma square over n, and the off-diagonal elements are independent normal variables of variance sigma square over n. And of course, W is symmetric. And then I define, given this quenched matrix, I define a measure over the spin configuration, P of x1, x2, xn, condition to W, which is proportional, so up to a normalization factor, to a hard constraint, or maybe, no, I should write it exactly. So it's a hard constraint that the sum over I xi squared should be equal to n. And then we have the exponential of 1/2 sum over I and j, xi, wij, xj. And I have a normalization constant here, which is called the partition function, which depends on the W matrix. Okay, so and what we found is that this model actually has a phase transition in the infinite n limit. So what happens is that as sigma is varied, we can actually track the evolution of another parameter, which is the projection of x over the along the top eigenvector of W, which I call E1, associated to the eigenvalue lambda1, which is with high probability equal to 2 sigma, right, with this semicircle Wigner distribution. And if you plot the dot product here, let's say the square, and this is the average of this, average of a disorder, then what we find is that this quantity is 0 up to, this is as a function of sigma, up to sigma equal 1, and then it grows, and it reaches 1 for sigma equal to infinity, and the equation here is 1 minus 1 over sigma. So this is what we found, saying that we have this cloud of points which have a small Gaussian fluctuation along most directions, but we have a localization with x1, I mean x1 being the projection here, of the order square root of n along so the top eigenvector of W. Okay, so now what I would like to do is to find back all these results, and more results actually, using the replica approach. So if you remember, the quantity which is crucial in the replica approach is the effective energy, which I introduced yesterday in the slides. So let me remind you of the definition. So the effective energy is something which is defined through this, which is defined implicitly through this thing. So this is essentially, so it's a function of, okay, so I will use the replica index A, which goes from 1 to small n, yeah, which is an integer number. And I will use notation with vectors, so x1, x2, xn. And these vectors are capital N dimensional vectors, which are, so this is a single x here. Okay, and the definition of this is that it's equal to the exponential. So we look at the, what we call in physics the Boltzmann wave, so the non-trivial wave here, which is biasing the measure, the uniform measure on the hypersphere. We look at it and we just use it for all replicas. So we have xia, xja, sorry, with a product over A running from 1 to n. And this whole thing here, so that would be the measure up to the normalization thing, up to the hard constraint that you would have for n independent replicas. And then we will average over the disorder, over W here, and that will create an effective coupling interaction between the replicas. So this is what I defined yesterday, if you remember. Okay, so what I would like to do now is to compute explicitly this effective energy, and you will see the effective interaction that is a trace of the fact that all these replicas were living in the same landscape defined by the same W. But of course, W will disappear. Okay, so we will use the fact that the model is very simple in terms of this distribution of the quench variables here. They are all independent from each other, so this average here can be computed very easily. So let me put the product over A inside the exponent here. So I have a sum over A and n, A running from 1 to n. And then I will use the fact, okay, Wij is a symmetric matrix, and then all the elements are independent. So this average here will be a product of averages. So I have a product over the diagonal element of exponential Wii, sum over A, xia, xja. Oh, I forgot the 1/2, sorry. And that should be average, right? So I'm using here the fact that all the diagonal elements are independent from each other. And then I have a product over the off-diagonal elements. And here I use the fact that the matrix is symmetric, so the 1/2 will go away. And I have a product over all pairs, I smaller than j. Exponential Wij, sum over A, xia, xja. Okay, and then it's very easy to do these averages because they are just, I just compute the Gaussian, the average with the Gaussian measure. So what I get is the product over I here of exponential, so the variance of W, 2 sigma squared over n times 1/2 times this term squared, sum over A, so it's an I here, xia, xia squared. And then I have the same kind of average, except that the variance is half of it for the off-diagonal elements. So exponential sigma squared over n times 1/2 times sum over A, xia, xja squared. Is it okay for the average? Yeah. Yes? Okay, so now you see the reason why I wanted to have the variance of the diagonal elements, which was twice the other ones. It just makes my life a little bit easier here because I can put back all these terms together into a single term, which is exponential of sigma squared over 4n times the sum over I and j of a sum over A. Sorry, I missed something here. There was a 1/2 here. Yeah, sorry, I missed the 1/2. There is a 1/2 here. No, that's, so what do I do here? So when I do the average here, I get 1/4, so there should be a 1/2, and here there should be a 1/2 or so. Sorry about that. Okay, and then so I get sigma squared over 4n, sum over I and j, sum over A, xia, xja squared. Okay. Okay, so I will rewrite this double sum here. So what I want to do is to really make appear these overlaps, these similarity measures I mentioned yesterday. And the best way to do that is to rewrite the sum square here as a double sum. So a sum over A, xia, xja can be written squared. It's the same thing as if I use another mute index, let's say call it B, which is another replica index. And I get xib, xjb. And this is in factor of this term, right? It's exactly the same thing. So now we have a quadruple sum, and I will exchange the replica indices with the site indices, and we'll see immediately how these overlaps appear. That is equal to exponential sigma square over 4n. We have a sum over A and B, and here I have a sum over I. So let me put together the x with the same index I, xia, xib, and I have exactly the same sum with the j index here, xja, xjb. Okay? Okay, so I'm almost done here. The calculation is almost over. What I will do, since the x's actually have a norm of the order of n, you know, these quantities will be typically of the order, they can be as large as n. In particular for A equal B, they will be exactly n. So it's nice to actually normalize this thing by 1 over n here, so to have quantities of the order 1. But if I do that, then I get the n here. Okay? So now everything is intensive in n here, and I have the explicit extensive contribution in front of the double sum over A and B. Yes? Okay, so this I will call the overlap, as we did yesterday. It's the overlap between the replica A and the replica B. And it's a function of x, which is the set of all my small n configuration. And obviously, this quantity is exactly the same, right? It's the same overlap, which is squared, right? Okay, so we see that at the end of this calculation, so maybe I should write it, I will write it here so I can erase. We have computed the free energy, the effective energy, sorry. And it has a very nice and very simple expression in terms of the overlaps between the different replicas, which comes from the very simple nature of this model. So what we have found is that exponential minus the effective energy between the replicas is going to be simply exponential sigma squared over 4 times n times the sum over all pairs of replicas A and B, QAB, sorry, I put replica index here, QAB of x squared, right, where QAB is simply, which is a function of all, is simply 1 over n xa dot xb. Okay, so we see here the practical implementation of the ideas of similarity. So you see that the measure is such that let's say the probability will be higher, or if you prefer, the effective energy is lower if the replicas are very similar, if the QAB are close to 1, which is the largest value you can think of, which is obtained when A is equal to B. Right? So we see this effective attraction between the configuration coming from the fact they were obeying at the same matrix W. Okay. So now the question is, how can we understand what is going on at the global level? Because it's true that this term here is trying to push all the replicas in the same direction to maximize this sum of QAB squared. But the point is that if we look at all possible configurations, all the possible x's, set of n replicas, there are not so many of them which are all equal, right? If you compare to the whole diversity of possible configuration you can think of. So there will be a kind of trade-off between these energetic terms which tries to push the replicas in the same direction on an entropic term which corresponds to the fact that they use a huge diversity of configuration, and naturally they try to be orthogonal to each other, right, on the hypersphere. So we have to understand how this trade-off between entropy and energy is actually realized. So what I need to do is to understand if I have all my configuration on the sphere. So this is the hypersphere, right? I have all this configuration of norm square root of n, x2, and so on. So what is the entropy of configuration which is associated to a given matrix QAB? What is the multiplicity of configuration which are associated to a QAB matrix, right? So essentially what I want to do is, informally, if I have an integral, and this is to compute z of w to the n, I have an integral over my n configuration, small n configuration, and this is given by this effective energy here. So I rewrite it as an integral over all the x's xn, exponential sigma squared over 4n sum over a and b QAB of x squared. Then you see I can actually, since the effective energy depends on the configuration only through the QAB, I will replace this integral over the configuration by an integral over the QAB matrices, but then I have to take into account the multiplicity of configuration which are associated to a given QAB matrix. So this is what I call the entropy. The entropy is just the log of this multiplicity. Okay. So we need to compute how many configuration x1, xn are associated to a given QAB matrix. So there are different ways. I mean, it can be done actually without any calculation, but let me try to do the calculation so that you see the outcome and you will say, yes, it's obvious that I should have written it immediately on the blackboard. But let's do the calculation, which is not very complicated. So in order to compute this entropy, I will compute one quantity in two different ways. And then by making the correspondence between the two expressions, we'll get the entropy very easily. So it's a very standard way of doing calculation, and we will use it another time today and more times in the next lectures. Okay, so let me consider the quantity psi of some matrix R. So I consider here n by n matrix. So with elements R, A, B, any matrix you want. Well, actually not exactly any matrix you want, but let's say a generic matrix, which is given by the integral over all possible configuration, n of them, dxa, of exponential minus sum over A and B, RAB, xa dot xb. Right? So for a generic matrix R, I can consider this integral. Of course, I need R to be definite positive if I want this integral to converge, right? But that I can define. So I will compute this integral in two different ways, and you will see how it gives us very easily the entropy. So what is the first way to compute the integral? So maybe I can divide the blackboard in two different parts. The first way is to do, okay, calculation here. So let me be explicit about this dot product here, the sum over the component. And you see essentially what I have here is just the same integral over all the components I running from 1 to capital N. So it's a single integral to the power capital N. So psi of R is just the integral over one component. Let's call it, let's say I just remove the I index. So it's dx1 up to dxn. So I keep only the replica index. Exponential minus sum over A and B, RAB, XA, XB. And this is to the power capital N. Okay, that's pretty obvious. And then this integral is just a Gaussian integral, so it's very easy to do. I'm assuming that R is definitely positive, otherwise it wouldn't make sense, right? So it's a Gaussian integral. The only thing with the Gaussian, usually you have a 1/2 here, right? So I will just put a -2 here. No, sorry, a +2, there was already a minus, sorry, I made a mistake with the sign. So I just multiply I by 2 to get the usual form for the Gaussian integral. So it's a Gaussian integral with here an inverse covariance matrix, which is twice the matrix R, right? So this, by you know the multivariate, you know how to do the normalization of a multivariate Gaussian distribution. This is simply 2 pi to the power n over 2 over the square root of the determinant of twice the matrix R. And the whole thing is to the power n. Yes?
Could you repeat what R is again?
Okay, R is the matrix that I choose. You will see what it means later on. But let me choose a matrix, RAB, which is on the same dimension as QAB. So far, it has no particular meaning, but it will acquire one very soon. So I just define one matrix RAB, which I like, which is just definite positive. And then I compute this quantity here. Okay, but do you agree that this expression is correct for any positive definite R? Yes? And then I will choose R in a nice way very soon.
Can I just ask, like, the x's are on the sphere, right?
So here they are not.
Oh, so your little xi's are...
Yes, here they are not.
So you're going to have to...
Yeah, I'm just relaxing everything. Okay, so that's one way to compute psi, but there is another way to compute psi. And the other way to compute psi is actually through the introduction, explicit introduction of the entropy I was mentioning with words just a little bit before. So I will, since, okay, so maybe I can, okay, if you look at how the measure here depends on the axis, you see they depend on the axis through the QAB. This is simply n times QAB of x. Okay, so that means that this integral here over the axis can be replaced with an integral over the QAB. And the QAB are defined for all a smaller or equal to b because it's a symmetric matrix. And then I have a product over the xa, so I will define the measure of the QAB. So there will be a product over all a smaller than b of the delta, Dirac delta, of QAB minus 1 over n xa xb. And once I have determined the QAB, I have set the value of the QAB through this equation, then obviously the measure here is simply exponential minus n, sum of the a and b, RAB QAB. Okay? It's just a matter, I have introduced the QAB here and I'm integrating over the QAB, right? It just, so it's not so far very interesting. But now the quantity here is what I call the multiplicity. It tells you what is the weight associated to a given matrix QAB, right, for all the elements A and B. And that, I would expect that it will scale exponentially with n, because I am in the n-dimensional space. And to the largest order in n, I will call n this exponential of n times s of the Q matrix. So it depends on all the elements, QAB. And this is called the entropy. So it's a log multiplicity if you prefer. Okay? And that's the quantity I would like to compute. Okay, but look at this. Now, where is the dependence in capital N? It's all, so obviously this expression is not exact. There will be some smaller terms here, but to the dominant order in N, I'm assuming this is the expression, right? So now look at what this integral here over the QAB. When n goes to infinity, we have a capital N here, and all the other quantities, the QAB, the RAB, are supposed to be finite, of the order 1. So I can estimate the asymptotic behavior of this integral using the Laplace method, right? It's just saddle point method if you prefer. You want to be more generic in the complex plane. So I will look for the value of QAB, which maximizes this expression here, and it will be the outcome to the dominant order in N. So that should be equal, when n goes to infinity, asymptotically to the maximum over the QAB of the entropy S of QAB. So let me write it just S of Q. Q is the matrix here, minus the trace of R dot Q. I mean, times Q. It's a matrix product here. So now you see the meaning of R, right? Essentially, it's not completely easy or obvious to compute the entropy, but it's very easy to compute its Legendre transform. And this is the usual trick in statistical mechanics, right? You jump from one ensemble to another one. So working at fixed QAB is not completely easy, but working at fixed pressure over QAB, which is trying to force the overlaps to have a definite pressure, a definite value, by imposing some pressure RAB here, is much easier. since this expression is going to be correct for all r's, then I can match this expression here with that one. This is true for all r. I can do the inverse Legendre transform, and I get the entropy QAB. So it's a very, very useful trick that you see over and over. It's just going from one ensemble to another one in statistical mechanics, right? Yes?
And then what is the measure of integration on the right-hand side in the outer?
Sorry, it's a D. I forgot the D. That's bad. So all these QAB, they are comprised between -1 and +1, right? Sorry about that. Missing D is a big issue. Okay? Okay, so let's do that. We are almost done. So now I can identify the two sides of this equation. They are equal in the large n limit. So that implies that the maximum over Q, so Q being the matrix here.
Sorry, real quick.
Yes?
So in that case, the x's were not constrained to be on the sphere.
No, they are not.
So why are the limits -1 to +1?
You're right. Well, I mean, I will be interesting, okay. Because I will be interested in the case where QA is equal to 1, but in principle, they could be anything, right? Okay. So there will be constraints, the values will be constrained by the r's here. So the value of r will put some constraints on the q, but so far it's not imposed. Once I impose QA equal to 1, then they will be all between -1 and +1. But this is not imposed yet, you are right. But this is the regime of integration where we will be interested in at the end. Okay, so we get that the maximum Q of S of Q minus trace of RQ is going to be equal to -1/2 log of the determinant of 2R plus some constant. And the constant is everything which is the 2 pi and everything that I don't care about, which is not dependent on Q and not dependent on R. And this should be true for any R. Okay, so we are almost done. So we know the Legendre transform of S, so we just have to do the inverse Legendre transform to get S. Yes, so, okay, I can erase here, I think. I will need it later. Okay, so, yes, please.
Were there trace of R times these two matrices? Is it Hadamard product between the matrices or just matrix multiplication?
It's matrix multiplication, right? Turns out that they are symmetric, so it doesn't change anything, but it's matrix multiplication. Okay, so so let me do just the inverse transform. So what I will do is that I simply differentiate this expression with respect to R. So if I by differentiation, so I'm starting from this expression here, this star equation. I'm jumping to the other blackboard here. And I will differentiate with respect to R. So that means differentiate with respect to some elements of R. Right? And what you get is, okay, on the left-hand side, if you differentiate with respect to R, you have on the left-hand side two parts in the derivative. One is the explicit part, the explicit dependence on R, which is given a minus Q if I differentiate the trace of R times Q. And the other one, remember all the matrices are symmetric here. And the other one is the implicit dependence on Q. But the implicit dependence on Q gives nothing because Q is such that the derivative with respect to Q is equal to 0 on the left-hand side. So you get only the explicit dependence, right? And on the right-hand side, I get the derivative of -1/2 log of determinant of 2R. So this is -1/2 times 2 coming from the 2R times the derivative or log of determinant of the matrix with respect to the matrix element, which is just the inverse matrix. Okay, so you see that Q is simply 1 over 2R. 1 over 2R means the inverse of the matrix 2R. Okay, so now since we have that, we can use this expression and put the expression of R as a function of Q. So that implies that S of Q is -1/2 log of the determinant of 2R, which is Q minus 1, plus the trace of R times 1 over 2R minus 1 plus a constant. But you see that this thing is actually a constant here. It doesn't depend on R, and it doesn't depend on Q, so we are left with 1/2 log of determinant of Q. Okay, so this is the entropy we were interested in. Is it okay for a calculation? Okay. So actually, it's something we could have guessed without any calculation. So why? Because we can use the maximum entropy principle here. So how does that work? We want to understand what is the entropy at fixed QAB. But what are the QABs? The QABs are just the second moment of the axis. So essentially, we are trying to compute the entropy of a distribution at fixed variance or even covariance. And you know that the distribution with maximum entropy, and this is what we want to get here, is going to be a Gaussian distribution. That you know for a single variable, right? For a real variable. You know that if you have a distribution, unknown distribution P of x, and you fix the mean and you fix the variance and you ask what is the distribution with maximal entropy constrained by that, it's going to be a Gaussian, right? So here we fix all the covariance elements, the QABs. So it's going to be the distribution with maximum entropy, which is going to give this entropy here, is going to be also a Gaussian distribution. And you know also that the entropy of the Gaussian distribution is 1/2 log of the determinant of a covariance matrix. So this is it, right? We have not found anything new here. But I think it's good to see the explicit calculation, maybe, if you're not convinced by the maximum entropy argument. Is it okay? Okay, so we have everything we need now. So I can continue my calculation. And I will do that. Can I erase this blackboard? Yes? Okay, so now let me go back to the calculation of z of w to the n, which was my starting point. Then this calculation was, okay, let me write the expression, so I need a better chalk here. Yes. So it was a product of a dxa. We have a delta of xa squared minus n, and then we have this exponential sigma squared over 4 times n, sum over AB, QAB of x squared. So now I can replace the integral of the x's by the integral over the QAB matrix, taking into account the multiplicity of configuration having a given set of overlaps here. And you see that this hard constraints here is simply imposing that QAA of x is equal to 1 for all A. So this has a very simple translation in terms of the overlap matrix, right? All the diagonal elements of this overlap matrix should be equal to 1. Okay, so I'm ending up with an integral over all the A smaller than B, dQAB here, and then I have an exponential n of S times the S of the matrix Q. So the matrix Q here is a matrix which is n by n, so with all ones in the diagonal. And you have the QAB here, and it's a symmetric matrix QBA here. Okay, plus sigma squared over 4. And here I have a trace of Q squared. Is it okay? So now again, what I will do is that in the large n limit, I'm expecting this integral to be dominated by the matrix Q maximizing the term within brackets here. So I will just write that the derivative of this term is equal to 0 for all the elements which are off diagonal. Not on the diagonal because they are fixed by constraint to 1. So I don't need to optimize over them. Okay, so let's compute the derivative. So maybe this thing here, I know the expression. So S of Q is 1/2 log of that Q. So the whole thing here, I will write it as exponential n/2 times some V of Q. And this V of Q is log that Q. I just factor out the 1/2 plus sigma squared over 2 times trace of Q squared. And I will need this definition of V of Q later on. Okay. Okay, so what I want to find is the maximum, is where the maximum of V is reached. So far, everything I've done is correct for integer n, right? And very large capital N. Integer small n and large capital N. So let me compute the derivative, dv over dqab. Okay, so we have to differentiate the log of determinant of q. This is simply q to the minus 1 ab. And then we have the sigma squared over 2, so it gives sigma squared times qab. And that should be 0 at the maximum. And that should be true also for all a smaller than b or for all a larger than b, whatever, but not a equal b. Okay, so we have to solve this equation. So it's an equation over the Q matrix. And now comes the interesting part. Is, everything here, here I have an integer by integer matrix. I mean, the size obviously is an integer. But I need to find an ansatz here, or a solution for this equation, which will allow me to do the small n going to 0 continuation. Okay, so what can we say about the solution of these matrices? So the obvious thing we can do is say, okay, all the replica indices here actually have no meaning. If I just do a permutation between x1 and x2, it doesn't change anything to my effective energy. It doesn't change anything to these things here, right? So in fact, they play no role. So that means that this expression here, this thing here, is completely invariant under a permutation of replicas, all possible permutation of replicas. So the simplest thing you can do, or you can assume, is that this invariance, this symmetry of the function you are optimizing is actually reflected in the solution at the maximum. That's a higher symmetry solution, right? So the solution we can look for, at least at the beginning, is a solution which is replica symmetric. So what is a solution which is replica symmetric? It means that QAB, the overlap matrix, which satisfies this equation here, has the same symmetry as the problem. That means that QAB should be equal to the same value Q for all A smaller than B. So it's a very simple matrix, right? The Q matrix is simply 1 on the diagonal and all Q's outside. I'm not saying it's a good solution. It turns out it's a good one here for this problem because it's simple enough. But it's a very reasonable assumption here. We just look for a solution with the same symmetry as the problem. It doesn't need to be true for all problems, right? You can have a problem with a high symmetry, and still you can have a maximum which are not symmetric. So take a very obvious example. You have a function which is an even function of some variable q, a single scalar variable. And for instance, it's an even function of q, so it can be this way. And then the maximum will be in 0. It has the same symmetry as the function. But it could be also this way, right? Which is perfectly symmetric also. And then the maximum is not in q equals 0. So we have to be a little bit careful about this assumption, right? But certainly, this solution here should be a saddle point. It could be a local minimum. It could be a global maximum. But it should be something, right? The derivative should vanish. Okay, so we just have to do a very small calculation here. So I will make this ansatz here and put it back here. So I need to know the expression of q to the minus 1. So you can check, but I want to just to give you the expression. So if q has this expression here, then q to the minus 1 has the same symmetry. So all the diagonal elements are equal to the same thing A, and all the off diagonal are the same, B. And just to spare a little bit of time, I'll give you the expression with for I, A, and B that you can check. So A is going to be equal to 1 plus n minus 2q over 1 plus n minus 2q minus n minus 1q squared. And B, the off-diagonal element, is minus q over the same denominator. So then, okay. So within this assumption here, then I have a single equation over Q, which is obtained by saying that the B element of this matrix plus sigma squared times Q should be equal to 0. Yes?
Why not apply the answer before?
I could.
Add the log determinant Q, then we don't need to calculate inverse.
I could, but I don't like it. No, I could. I mean, it would give exactly the same result. You are enforcing by hand this and that here, so it would actually make your life a little bit simpler, which is nicer. The problem is that in principle, this is not what you should do. You are in the QAB space. Then if you want to be safe, then once you have the saddle point equation, here you make an ansatz, and then you can check whether it's locally stable, whether there could be other ones. So if you do it from this point here, then you have to redo it for another ansatz, right? I want to do the job only once. Okay. Okay, so we end up with a very simple equation of a Q. So I take just B, which is minus Q over 1 plus, so I can factor out 1 minus Q. Actually, you see Q equal 1 is a 0 here of the denominator. Okay, so it's 1 minus Q times 1 plus n minus 1Q plus sigma squared Q should be equal to 0. Okay, and now we have to solve for Q. And you see there is an obvious solution, which is Q equal to 0. So we get Q equals 0. Or we can divide by Q, and then we get an equation for Q by saying that the minus 1 over this should be equal to sigma square, plus sigma square should be equal to 0. And the other thing is when n goes to 0, I can do it when n goes to 0, which is the interesting limit for me so far, is 1 minus 1 over sigma. You just do n equal to 0 here, you get 1 over 1 minus q squared, which will be equal to sigma squared. So when you solve, you get this. Okay, so we get two solutions, and now we have to decide which one we should choose, right? So how do we decide that? Well, we have a principle for that, which is we should maximize our function v, which was on this blackboard, and then I erased it. So we have to maximize v. So remember what v was. Maybe I can write it here. V was the log of determinant of q plus sigma squared over 2 trace of q squared. So what I will do now, I will write v of q. And so we have q. So we can compute the values here and see what is the top one, right? And this is the one we should choose, in principle. So if we look at the expression of v, so I will v of this QAB matrix, which is 1 on the diagonal, q out of diagonal. If you do the calculation, that gives you log of the determinant. So what are the eigenvalues of this matrix? You see the all 1 vectors is an eigenvector of eigenvalue 1 plus n minus 1q. So we get a plus log of 1 plus n minus 1q as the first eigenvalue. And then the other eigenvalues are, you choose one for the top component here, the first component, and then you have all the other components are zeros except one of them, which is minus 1. And you see they are all equal to 1 minus q, and there is a degeneracy, which is multiplicity, which is n minus 1. So you get this. And then we have a trace of q squared, which is easy to compute, and we get sigma squared over 2. The elements on the diagonal of q squared are simply 1 plus n minus 1 q squared, and we get n elements to get the trace. Okay, so this is our potential, and I would like to maximize it, but I do that when n goes to 0. So we have to be careful, because if I blindly do n equal to 0 here, I get nothing, right? I get something which does not depend on q, because I have 0 replicas. It's z to v0. It should be actually 1. So if I expand this for small n small, which means I expand this potential here to the first order n, I get n times v of q plus O of n squared with v of q, which is given here. I don't know if you can read it. Can you read it from? Yes, if I. This is, you just do the expansion to first order, and that gives this. Okay, so the first thing we see is that when n goes to 0, as I said, this potential v is going to 0, which is nice, actually. We need that, because remember, we wanted to compute z to the n. Z to the n, when n goes to 0, should be 1. And this is given by exponential capital N over 2 times the potential v. So it has to vanish when n goes to 0, and it does. So this is nice. Now, our prescription is that we should maximize this thing here. So if you look at the equation v prime of q is equal to 0, you find back a saddle point equation. You find back a maximization equation, which is exactly the same with n equals 0, and you find back these two solutions. So this is consistent, right? But now we know the two solutions. We will put them here and look at what it gives. Okay, so we have to check the value of the potential for q equals 0, and for q equal to 1 minus 1 over sigma. Okay, so it's easy to do to put back q equals to 0 in small v of q. So v of 0 is sigma squared over 2, and v of 1 minus 1 over sigma is 2 sigma minus 3 halves. You can check that. I hope I didn't make any mistake. Log 1 over sigma. Okay, so let's plot these two candidates here as a function of sigma and see what happens. This is sigma. So the first one is sigma squared over 2, so it's very easy. It's just a parabola. This is v of 0. And the other one diverges when sigma goes to 0. It goes to plus infinity. Okay, and it actually crosses this curve here, and then it grows as sigma, so it's much lower than below the parabola, and this is the other one. And they cross here, and guess what? Sigma equal 1. Okay? They have to, right? Well, 1 minus 1 over 1 is 0. Okay. But now we are in big troubles, because if we look at that, we see that if we want to maximize, we should choose this solution, 1 minus 1 over sigma for sigma smaller than 1, and that one, q equals to 0 for sigma larger than 1, which is obviously wrong. But obviously, I mean, something is wrong in our reasoning, because we see that it's very shaky. We want to maximize, but look, we send n to 0. So if I want to maximize this big V here over q, if small n is positive, then I need to maximize V of q. But if I send n to 0 by negative values, then I should minimize V of q. So we see that the sign of the number of replicas, even if we reach the same value n equal to 0, is actually changing the solution we should actually select, right? So that means the fact that we maximize or minimize should depend on the value of n. In fact, we see that also in a safer regime, because n equal to 0 is a bit tricky, but you can look at what happens for integer n. So the last integer which is possible, but we understand very clearly, is n equal 1, right? So let's look at what happens in the vicinity of n equal 1. So for n equal 1, if you look at this potential here, then you find a potential which is simply something which is independent of q, right? And it cannot depend on q, because, I mean, z to v1 is actually something which cannot involve the overlap. You have a single configuration. There cannot be any dependence on the overlap. So if we want to get something non-trivial, we have to be in the vicinity of n equal 1. So we can expand also the potential for n close to 1. And let's do that to see what it gives. So if I look at what happens for V of Q on n in the vicinity of n equal 1. So I just take my formulas here. If I find them back. Okay. Yeah, okay. So this is sigma square over 2, which is independent of Q, plus n minus 1 times some term, which is Q, plus log 1 minus Q, plus sigma squared over 2, 1 plus Q squared. And then you have terms of the order n minus 1 squared. So this is an easy, I mean, you can plot this potential very easily. You just look at this term here, and I'm just doing a sketch of this thing as a function of Q. So, and what you get is that if sigma is smaller than 1, this is a decreasing function of Q. So it gives something like that. This is for sigma smaller than 1. Of course, the curve depends on sigma. This is just the general behavior, right? And now, if sigma is larger than 1, what you get is a nice maximum somewhere for Q large, I mean, far away from 0. So we see clearly that when n is larger than 1, so it reaches 1 by positive value, I mean, by values above 1, which is the safe regime where we want to consider integer n, we know what it means, then we have to maximize V in order to find something interesting, right? And it is exactly the regime where we are. But as soon as we go below n equal 1, if we want to track this solution here, then we have to reverse the prescription. We don't want to maximize anymore, we need to minimize. And essentially, the reason is that if you look at the number of degrees of freedom over which we maximize or we minimize, it's 1/2 n times n to the minus 1, and this number changes signs when we are in between 0 and 1, or if we go to negative values of n. So the maximization becomes a minimization if we want to track the solution. So this is one of the oddities of the replica approach. Okay? And that you can see also if you look at the, I will comment on that, on the Hessian matrix. Okay, so if we accept this and we see that in between 0 and 1 we should actually minimize and not maximize, then we are safe. That means that we should find Q equal to 0 here, and above sigma equal 1 we should get this solution, which is 1 minus 1 over sigma. And this is exactly what we found yesterday with the true solution, you know, without any replicas, right? So remember what we found yesterday, which I just remind you about at the beginning. We had this overlap between x and E1 squared over n, which was, let's do the overlap this way, which was 0 up to sigma equal 1, and then was square root, this is 1 here, of 1 minus 1 over sigma. So what happens, it means that if you look at your space, this is the direction E1, then a typical configuration, X, here, will have an overlap which is very strong and large of the order square root of n with this vector E1. So it lies on a cone of axis E1, okay, with an angle which is just that the dot product is this times square root of n. Now throw two configuration X and X prime. Another one will be on the cone also. They are just independent. And you ask what is the dot product between two things which are on the cone. And it's just the square product that they have with the axis, right, in high dimension. So you get this squared, which is exactly the cube we find here. And if you are below sigma equal 1, then we know that we don't have this localization on E1, so it's just 0. Do you agree on that? Okay, so what I'm saying, if you want, we can just say it in a more, maybe I will erase this part here. So I want to be a little bit less fast on this point. We know from what we have done yesterday that X is typically something which is this dot product here. So square root of n times 1 minus sigma 1 minus sigma times E1 plus something which is orthogonal. So it's a combination of E2, E3, and so on, with Gaussian values here, Gaussian projections, which are all of the order 1 in terms of variance, right? So I don't write them, but they don't matter. Now, if you take another x prime, it will be the same thing, plus something which is totally unrelated. So when you do the dot product between these two things, you see you get exactly, and you divide by n, you get exactly this q which is here, in the regime sigma larger than 1. So you see, we find back exactly what we should find. So the replica solution is completely correct, right? So it's nice that you can see the total matching between the two approaches. Okay. Can get rid of that. Okay, so I would like to make some remarks now. There are a few important remarks, and to go a little bit further, using this solution, what we have found, try to exploit it to squeeze the lemon, because we have done an exact solution. I mean, we have a nice solution for any n, not only n equal to 0, so we'd like to use it as most as possible, right? Okay, so there are some remarks. So first of all, and this is related to the question you asked, I mean, I just say, okay, let's look for a solution which has the highest possible symmetry. So it means all the off-diagonal elements of QAB are equal to Q. We are lucky here, the model is simple, it gives the right things, we are very happy, everything is nice. But in general, you know, when you don't know the true solution, you don't know, then you end up with something. The question is whether something is true or it's just wrong, right? It could be. So there are different ways to try to know the outcome, whether it's true or wrong. And I just want to mention what could happen, even if it does not happen here, right? But it could happen, and it will happen in more complex models that we will see. Okay, so the remarks. Okay, so the first thing is that any replica calculation, and I was told so by my supervisor, that who is a very knowledge person in replicas, is that when you do a replica calculation, that is not sufficient. You should always check the stability, right? So what we had here is that we had found V of Q. So what we had done, we had solved dV over dQAB is equal 0. That's obviously a solution if you want to, let's say, optimize, maximize or minimize. That's obviously you have to do that. But then you have to check that it's consistent. So if we want to minimize, then we should check that the Hessian matrix HABCD, which is the second derivative matrix, that should be positive definite or negative definite, depending on whether your number of replicas is in larger than 1, smaller than 0, in between 0 and 1, and so on, depending on when you are, where you are. So you should check this, compute the eigenvalues, and check they have the right sign. So you are really looking at a minimum or a maximum. And in fact, as you move the control parameters, for instance, sigma here, the sign may change, and this signals the onset of some replica symmetry breaking. That means the solution you were tracking is not correct anymore, and you have to look for another solution, right? So I won't do it here because that does not happen. I mean, we can compute the eigenvalues. It's an interesting calculation. I don't know whether I should do it, actually, maybe for a more sophisticated model. Maybe I should. Okay, I'll try. But okay, that's something we should do, first thing. Then, of course, even if it's locally stable, that doesn't prevent the existence of other solutions which are completely far away in the QAB space. And in fact, even in this model, there are other solutions. And I'm slightly surprised you did not complain about here, because actually, in the model we have, I could have also here a projection exactly in the other way, right? We know that only the sign is fixed. So which means that there could be a minus sign here and a plus sign here. You know, I could have negative Qs and so on. So in fact, in these particular very simple examples, we have found one solution QAB, But there are other matrices which are exactly at the same level of quality. They give exactly the same value of V, and they are perfectly nice solutions, where you can choose for any replica. What you can do is define a sign, SA, which is plus or minus 1, which corresponds to the projections along E1 here. So I'm cheating here. I'm using my knowledge of the exact solution of the problem, right? But this is the interest of this model, right? I can choose that, and then it means that the QAB I have found would be changed into SA SB times QAB. Right? It's another solution of the problem. And in fact, you can check it gives exactly the same V, exactly the same contribution. And why does it so? Because remember what V was? V was, okay, it's cancelled, but it was, first part was the log of the determinant of Q. But obviously, this matrix and this matrix, they have the same determinant. You know, you just multiply the product of ESAs and product of ESB, and just the product of S squared, so it's just 1. And they have the same trace of Q squared also. So they give exactly the same V. So in fact, we don't have a single solution, but we have 2 to the n, which actually does not matter at all when capital N goes to infinity, but we have different saddle points, right? Different or minima, to be more precise. So we should be careful about these possible symmetries. And then there can be much more interesting cases where actually the symmetry is broken. Let's say the replica symmetry is broken. Nothing that the ansatz I had made that all the off-diagonal elements were equal, this is not going to be true anymore. There would be some more interesting structure off-diagonal here, and we will see examples where this happens, right? It's not the case here. But in fact, this can happen, and it's a very important fact. Okay, so these are the first remarks. And then I want to do another remark about the value of n going to 0. So everything we have done so far, yesterday, when I did the introduction about replicas and all the calculation, we have used n as a parameter, but eventually n was sent to 0, right? In fact, this is the interesting regime, but it depends on what you want to capture. So now I want to extend our calculation, or let's say to extend the interpretation of our calculation to n different from 0. Okay, so what could be the interest of doing that? Okay, so let me go back to the partition function of our model, z of w, the normalization factor. This is the integral over one configuration with the hard constraint of exponential 1/2 x wx. And x and w, sorry, here was the GOE with the variance sigma square over n for the off-diagonal elements. Okay. So maybe what I will do now, I will simply is take variance 1 over n and then multiply this by sigma here. Do you agree it's the same thing, right? It's just a rescaling, right? So now it's nicer because I have an explicit dependence on sigma. Okay, so this depends now on the W, which is one element of this GOE ensemble here, and also on my parameter sigma. So you see that sigma is playing the same role as 1 over the temperature, and that I already said yesterday, but we see it explicitly here. Now suppose I take large values of sigma, not infinite, because I have to be very precise about the order. We always do capital N going to infinity first, and then we can do low temperature or whatever we want. But let's say I take large sigma here, and then we'll be more precise about what that means. Then that should be, when sigma is large, you see that the value of x which will dominate these things are the one which are along E1, the top eigenvector of W, right? So I would expect that when sigma is large, that should become something like exponential sigma over 2. So I get lambda 1, which is the top eigenvalue of this matrix here, lambda 1 of W. And then, of course, I get a capital N, which is due to the norm of X. OK, so we know that lambda 1 of W, as we said yesterday, if I look at the distribution of lambdas for this GOA matrix, is very close to sigma. And there can be fluctuations of the order n to the minus 2/3, right, which are well characterized for the fluctuation of the top eigenvalue of a random matrix. But that doesn't mean that it's not possible to have values of lambda which are much larger. So this is the lambda 1 here, distribution of lambda 1. So on average, this is 2 sigma, but it can fluctuate here. But for some particular realization, you can have actually values of lambda 1 which are much bigger than 2 sigma or much smaller than 2 sigma. This is still possible, right? It's a random variable. So in fact, there have been a lot of works in random matrix theory on the large deviation of lambda 1. So I don't know, maybe some of you are familiar. I saw yesterday in the flash talks, in the presentation, that some of you were experts in random theory, in random matrix theory. So maybe, and some people were actually experts in random matrix theory and in large deviations. So you probably know better than me what I'm going to say. But so what is interesting is what happens here on the flanks, right? So it's possible, but very unlikely, but possible, that the value of lambda 1 I have for my particular sample is going to be much larger than 2 sigma, right? So what does that mean? That means that if I look at all the eigenvalues of my matrix, and they are very dense here, close to 0, and lambda 1 is here. If I want lambda 1 to be much larger, I should actually try to pull it away from 2 sigma. And this is not so easy to do. It will cost me something in terms of probability. And the cost in probability will be exponentially, so the probability will be exponentially small in n, times some function phi of lambda 1 here. So why is it exponentially small in n? Suppose you have your matrix W, and if you just pick up randomly, then it will have a lambda 1 very close to 2 sigma, right? Now say, OK, I would like to modify it by hand in order to have a lambda 1 very different, much higher. So what you can do is to add to W something which is in the direction of E1, right? So what you can do is to do something like, E1 transpose, E1, and then you will add something, right? Some A here. So in order to have the right scaling here, you can see that it will actually change the trace of W squared. So I go from plus something of the order of n, if you do the calculation, right? So because the E1 here are of the order 1 over square root of n, if it's a normalized vector, right? So same thing here. So all the elements will change by the order of 1 over n. And since you are summing n squared such elements, then it will make a change of the order of n to the measure of W squared. In the GOE, that's exponential minus a trace. So this explains why you get here, hand-waving explanation, why you get an exponentially small in n probability of having a lambda 1 which is different from 2 sigma. So it turns out that this function here, which is this rate function for the large deviation principle, is completely known. And I just give it. So where do I give it? I can give it here. Phi of lambda 1. OK, so this is lambda 1 over 2, square root of lambda 1 over 2. So sorry, I shouldn't put the sigma here because I'm GOE with the sigma 1. Sorry about that. It's 2, right? Lambda 1 squared minus 1 plus log of lambda 1 over 2 minus lambda 1 squared over 2 minus 1. And this was derived, to my knowledge, first by Majumdar and Vergasola in 2009. Okay? So this can be exactly computed. And the reason why it can be exactly computed is that for the GOE ensemble, you can write down the full explicit joint distribution for all the eigenvalues, which is exponential of essentially the sum of the eigenvalues squared, which come from this term here, plus some log of van der Monde determinant, which come from the change of variable when you integrate over the orthogonal matrices to go to the diagonal form, which is a sum of a log of the pairs of eigenvalues, log of the absolute values of the differences of the lambda I minus lambda j. So you can really have a completely control over the joint distribution, and then you can compute this explicitly. I don't want to do that because it's completely outside my lecture, but it's a very nice thing. So you can ask here also what is going on the left side, which is very interesting. Actually, what is going on the left side is much more interesting than on the right side. And why is it much more interesting? Because you see it, right? If you want to increase lambda 1, that's easy to do because you just have to stretch lambda 1 using that. Now, if you want to move lambda 1 to this direction, that's really bad because you have to push all the eigenvalues. So one way to do that is, for instance, to shrink all the W's. If you shrink all the W's, you see that the trace of this thing here is going to be changed by order n squared, not order n. So it's much worse on this side. It's exponential minus n squared psi of lambda 1. And the psi lambda 1 is actually a well-known function. Again, it was derived by Majumdar and Dean in 2008, I think. I don't give the exact expression here, but it will be my contribution to the open session problem. OK, so it's known, right? But let me concentrate here only on this side, which is easier. So can we find back phi of lambda 1 from our replica calculation? That's what I would like to do in the last 20 or so minutes. No, I don't know how. I have 15 minutes, right? 15 minutes, yeah, sorry. 15 minutes. Yeah, sorry. 15 minutes. OK, so what is the connection between our replica calculation and phi of lambda 1? So on the right side. Until the connection is clear through this expression here. You see that z of w is essentially exponential of lambda 1. OK, so by computing the moments of z of w, we'll have the information about the statistical distribution of lambda 1. And that we do with a non-equal to 0 number of replicas. Yes?
Just a quick question. So how can you still have the n in that exponent? Like, like you have to wait by the overlap squared between a typical vector x and the top eigenvector, right? Doesn't that cancel the n?
You mean from here to there?
Yeah.
Oh, OK. So it's just that, this thing here, I'm just saying that this thing here, when you take, OK, WE1 is lambda 1 E1, right? So now if you do E1 here, you get E1 squared. And since I have this measure here, I get the n lambda 1.
But then you have to do it for a typical x and the overlap between a typical x and E1.
Here, I'm pushing, this is true only if I'm pushing sigma to very large values. If I'm pushing sigma to the very large values, you see that so I am on the hypersphere, and there is one direction, or the opposite one, actually, along E1, which is maximizing this quantity, right? The quadratic form is maximized by E1. I mean, x along the direction of E1.
Okay, I see.
So this is true only, I should be careful here. This is what I meant, right? When sigma is large, this is true. And in fact, you see what is important is that you have lambda 1, you have lambda 2. So it should be that sigma is such that sigma times the gap is very large, right? And so you can erase, you can forget about the other. OK, so let's exploit our calculation we have done so far. So now if I do z of wn, but I'm not considering that n should be equal to 0. It can be any small thing, and you will see how it should scale. Then this is exponential of n over 2 sigma lambda 1 of w times small n average, if sigma is large. Again, don't pay too much attention about what it means. I give you, so it should be larger than 1 over lambda 2 minus lambda 1, but sufficiently large, it should be true. OK, so now I'm using again, the knowledge here. I'm always cheating. I always know the answer before I do a calculation, so it's much easier, right? So I know that lambda 1 can have large deviation here. So that should be equal to the integral of lambda 1 exponential minus n phi of lambda 1. And you see, if the number of replicas n is small and positive, this quantity will be exponentially large in capital N, so it will really push my eigenvalues to very large values, much larger than 2. This is what is going to dominate the nth moment. Plus capital N, small n, over 2, sigma, so times lambda 1. Right? So now, again, this expression should be dominated by a value of lambda 1 which maximizes the exponent here. So I can put a n in front of, maybe I can factor out n. It's going to be easier. And I want to maximize this over lambda 1. So it's going to be exponential of n times the max over lambda 1 over of n sigma over 2 lambda 1 plus minus phi of lambda 1. But that we have calculated, and we know that this is exponential capital N over 2 V, or let's say the max over Q. You know what? I will write the optimum because we never know whether it's a max or a min. Okay, I will write an optimum. It depends on N, obviously, of V of Q. And of sigma, of course. And of n, the number of replicas. Here I am, okay? So again, what we have that this V we have computed with the 1/2 is nothing but the Legendre transform of a large deviation function of a top eigenvalue. So since we have V, we just have to do the inverse Legendre transform again, and we'll get back to phi. Okay, so this is what I would like to do in the last 10 minutes. You do the explicit, and then I will come to my open problem. So if we want to have a Legendre transform, then I need the parameter for the Legendre transform. So that I will call mu. So which means I choose, if you prefer, I choose a number of replicas, n, which is 2 mu over sigma. Well, it's not an integer number, but it's not worse than 0, right? Just a real number. So it will be small because sigma is large, and mu will be of the order 1 typically. But it's not equal to 0. And in principle, it could be positive or negative. Okay, so what we have to do is to go back to the expression we have for V. And we have, so one, if you, I erased everything, but I think you have this on your notes. So we have the minimum. So it's going to be a minimum over Q because this number of replicas, for instance, if mu is positive and sigma is large, is going to be close to 0. So between 0 and 1, so it should be a minimum of the potential that we had for Q and n equal to 2 mu over sigma. And if you go back to the expression we have derived before, yes. So where did I have it? Yeah, okay, so let me just finish it and then I will go back to the expression. So that should be the max over lambda 1 of mu lambda 1 minus phi of lambda 1. So the Legendre transform of phi. Now we can exploit what we have done before. And we have an explicit expression for V. Let's do that. So first I will, so I want to compute this V. So I need first to know the value of Q. So remember the saddle point equation for Q was 1 over sigma squared is equal to 1 minus Q, 1 plus n minus 1 Q. And this is how I got Q equal to 1 minus 1 over sigma when n was going to 0. This is what I solved. Now n is not equal to 0. N is 2 mu over sigma, right? So for n equal to 0, we have Q equal to 1 minus 1 over sigma. So here now I will have n not equal to 0 but small since sigma is large. So I'm expecting that actually q will be close to 1. So I will write, I expect q to be close to 1 with the same scaling. So q to be 1 minus some delta of a sigma, where delta will be a non-trivial function of mu, well, which is 1 for mu equals 0. So I put back this inside the equation here. And what I find is that this should be equal to delta of mu over sigma times delta of mu plus 1 plus mu, sorry, plus 2 mu over sigma plus correction of order 1 over sigma squared, I don't care, when sigma is large. I'm just replacing q by the ansatz here, right? So sigma is large, so I know that q should be close to 1 because they should project onto E1, the top eigenvector of W. So it will be very close to 1, and we know how it goes to close to 1. It's the correction are 1 over sigma. So if mu, the number of if n, the number of replicas is small, I expect the same scaling, and in fact it works, you see. I get the same scaling in sigma on both sides, so it's nice. So you get delta from this. So that means 1 is equal to delta times delta plus 2 mu, right? Which means that actually delta is square root of 1 plus mu squared minus mu. So again, for mu equals 0, we find back delta equal 1, which was our solution. But now we have a full set of solutions for a non-zero number of replicas. And you see, you can put mu equal mu positive here or mu negative, and it's perfectly fine, right? So now we know q as a function of sigma, so we can put it back here, and we get the expression. So let me write it here. When you do the calculation, you find that this is equal.
Sorry.
Yes?
This works also for mu negative?
In principle, yes.
We should have done the max over because mu negative means negative number of replicas.
So the max here is still okay.
No,
But here I should have, yes. But you know, when this expression was simply dv over dq equal to 0, right? But I agree, you should always keep in mind that you do a max or a mean, right? But dv over dq is the same expression, right? Yes?
So you chose that solution because the other one doesn't have the like limit?
You mean q equals 0?
Yeah.
Yes, it doesn't work when sigma is large. We know that, right? It's not the right solution. So for large sigma, I expect to be very highly condensating along E1, right? So that's the right solution to track. Okay, so I just have to do the calculation. So maybe let me do the calculation. Still have 5 minutes. So this 1/2 potential of q equal to 1 minus square root of 1 plus mu squared minus mu over sigma, and number of replicas n equal to 2 mu over sigma. Then you put back this in the expression of v we had. So this is 1/2. I do the full calculation. Log of delta plus 2 mu over sigma. So I do sigma large. Plus 1/2. So we had a n minus 1 times log of 1 minus q. So it's a log of delta over sigma. And then we have the sigma squared over 2, so there was a 4 here times 2 mu over n over sigma times 1 plus 1. Okay, so it's 2 delta. This is the 1 plus n minus 1 q squared here. We had in the trace of q squared. That gives, when you do the calculation, 2 delta plus 2 mu over sigma. I'm skipping a few intermediate steps, but if you have a problem with this is very elementary algebra here. If you have a problem with these steps, just let me know. We can do them more carefully. And if you do that, you find that this is going to, when sigma is actually going to infinity, it reaches a well-defined limit, which is the log of square root 1 plus mu squared minus plus mu square root of 1 plus mu squared. So this is very nice because we have our left-hand side here. So we just have to do the inverse Legendre transform and we should get back phi. Is it okay?
Is the rate function a strictly convex function?
Yes, it is. In this case, it is. On this side, yes, no problem. Okay, so so let's do the inverse transform, and then I'm done. So I erase the top part here. Okay, so what we do, I will simply differentiate with respect to mu here. So if I differentiate with respect to mu, I get, on the left-hand side, I get lambda 1. On the right-hand side, sorry, it's lambda 1. On the left-hand side, I have to differentiate with to respect to mu. So it's a d over d mu log of square root of 1 plus mu squared plus mu square root of 1 plus mu squared. So that is easy to differentiate. And you get that this is twice square root of 1 plus mu squared after simplification. Or if you prefer, that means that this is equivalent of mu equal to square root of lambda 1 over 2 squared minus 1. So here we see a first thing, which is a little bit annoying, but I mean that we could have predicted. Whatever the sign of mu, I cannot go below lambda 1 equal 2. I cannot reach the left part, right? And the reason is that there is this huge asymmetry between the right part, which is nice. It decays, the probability decays only exponentially in n, while the left part is decaying as exponential minus n squared, which is much worse, right? So I come back to that. Okay, so you get mu here, then you put back mu as a function of lambda 1 there, you subtract mu lambda 1, and you get phi of lambda 1, and it works. You find back the phi of lambda 1, which I wrote on the blackboard. Is it okay for the procedure? Yes? Or you want me to do the calculation? Or? I cannot because I have only 30 seconds, and I want to give the open problem. So is it okay? So you get back phi of lambda 1. I check, it works, I'm not cheating. Okay. So it's nice, and it's okay, everything is nice. So we get back to what Majumdar and Bagasola did 13 years ago, so it's not a feat, but you know, it's nice to see it. But now the open problem is what happens on the left side, which is interesting, right? So on the left side, that doesn't work, and the reason is that, so what have we done here? We have a nice relation here between, so lambda 1, so we are looking at eigenvalues here. Again, this is 2. This is the distribution of lambda 1. We are looking at lambda 1 here, which are well above 2 by some finite amount. It's very unlikely, very tiny probability, exponentially small in n. But actually, these matrices are typical of what you would get if your number of replicas is not 0, but it's shifted away from 0 by 2 mu over sigma. So it's just a way, I mean, we are replacing, let's say, atypical situation by a typical situation you get when you have a finite number of replicas, right? This is the idea of this Legendre transform. Now, if we want to go on this side, well, in principle, the procedure is the same, right? Here we have exponential minus n squared psi of lambda 1. So if I go back to my formalism, z of w to the n, that is going to be exponential, the integral over lambda 1, and it's exactly the same thing, and psi, n squared, sorry, psi of lambda 1 times exponential n over 2 and sigma lambda 1. So if I want to do that here with lambda 1 smaller than 1, in order to be comparable to that, you see, I need a number of replicas here, which is going to scale as minus a times n, where a is a positive number. So I could, in principle, apply the replica approach, but with number of replicas which scales with capital N. And this is tough. So this is my contribution to the open session, to the open problem session. So there have been some work on that, but it's still an open problem, to my knowledge. So there is a work by Parisi and Rizzo, 2009, where they looked at this problem, but only in the case where this mu, this A here is very small, but it's other one, and there is a capital N here. So why is it very difficult technically? Because now we cannot use the saddle point approach anymore, right? Because the dimension of a QAB matrix is the same as the capital N things that we send to infinity, so we cannot use saddle point as usual, right? So to my knowledge, it's an open problem to find with the replica method the large deviation on the left side. Okay. So I stop here.